All right, welcome back. As I said, I like to keep the videos 10 to 15 minutes just so it gives you a nice stopping point. So just as a quick review, we went through classification here. We went through mixtures, different types of mixtures, right? And we went through these slides. And again, you can go through these slides along with the videos. Now let's talk about pure substances. So a pure substance can either be an element or a compound, but the key is, unlike a mixture, a pure substance is one thing. It's got one set of properties, where a mixture has more than one set of properties. So if I have salt water, for example, the salt acts like salt and the water acts like water. Okay, here obviously. But if I have a pure substance, it has one set of properties. So let's talk about the two types of pure substances. So elements are the fundamental substances. They cannot be broken down to simpler substances. They're the building blocks of all substances. And I'm going to say it now. The smallest piece of an element is called an atom. So you can write that down as a definition. The smallest piece of an element is an atom. The smallest piece of an element, that is still that element. Okay? The smallest piece of gold is a gold atom. The smallest piece of iron is an iron atom. Now, the elements are interesting because they're all on the periodic table, and I'll post a nice one on the website, probably under the useful information module or somewhere, and you should probably print one or two and have them around the house. You're going to need them for your exams. I'm going to assume on an exam that you have a periodic table at your fingertips, so it's very convenient. This one doesn't have the names, so I'll give you one that has the names. However, your textbook has periodic tables in a number of places, the inside front cover, for example. And one thing you'll notice about these, and when I first saw this, I thought, what a weird way to arrange this. And we'll talk about this at length. You know, I wondered, what do the numbers mean? How come it's shaped like this? Why isn't it a nice rectangle? Right? Obviously, they're not in alphabetical order, but we'll talk a little bit about the symbols. Okay, but for now, anything that's an element is on the periodic table. If it's not on the periodic table, it's not an element. I'll spend a lot of time. So each element has an abbreviation. Symbols have either one or two letters, and if there's more than one, the first is capitalized. So punctuation is important, right? Because if you write C, big C, little o, that's an element. It's right here. See that? If you have big C, big O, that's two different elements. That's carbon monoxide. It's a compound, and we'll deal with that later. But you see that there's C and there's O. So if you've gotten a little sloppy with your writing, you know, if I ask you to write something and I want see this and you write this, it's incorrect. All right. Also, you'll notice some of the symbols seem to make sense. You know, carbon, nitrogen, but then some don't. Sodium is Na, potassium is K, and that's because many of them are from other languages, specifically Latin. All right. Now, a compound is a pure substance, but it's two or more elements combined in such a way to have one set of properties. So if I take hydrogen and oxygen, okay, and I put them as a mixture, the hydrogen will act like hydrogen and the oxygen will act like oxygen. But if I form a compound from hydrogen and oxygen, it's not hydrogen and it's not oxygen, it would be water. So it's got one set of properties. So it's not a mixture because the things it's made from are not what they were before. It's lost those properties have changed. It's one thing. So if you want to use very simple language, a mixture, several things in the same container. A compound is one thing made from more than one thing. An element is just one thing made from one thing. Now, compounds are represented by formulas. We'll deal with formulas a lot more later, and how to come up with them. But for now, we're going to get to just what do they mean. And so a chemical formula is going to have the symbols of the elements, and it may or may not have subscripts. Usually it will. And the subscript goes with whatever immediately precedes it. So in this case, right, water, but there's two hydrogens, one oxygen. We simply don't write ones. All right, so just to see some examples, this compound has 3 carbons and 8 hydrogens. Try this one on your own. Give yourself a second or two. And you're right. There are 3 hydrogens. There's 1 phosphorus and 4 oxygens. Sometimes we have parentheses. You'll see as we progress why don't we just write it a different way. But there's a good reason for that we'll deal with later. But try this one on your own for a moment. How many of each? Hit pause. All right, here we go. There's 2 aluminums. the parentheses the subscript distributes through. So that means there's 3, just like in math, right? There's 3 of this, and then 3 times 4 is 12. Why don't we write S3O12 instead? There's a good reason for that we're not going to get to today. So you're going to have to stay in the class long enough just to find that particular thing out. All right, so just as a review, right? An element is one thing made from one thing. Smallest piece of an element is called an atom. A compound is one thing, but it's made from more than one thing. Okay, and a mixture is just a bunch of stuff in the same container. Putting everything together, I think this is a little bit confusing, but we have solids, liquids, and gases that we talked about. So remember, and think in terms of the particles: constant volume and shape. Particles vibrate and interact strongly. Liquid, constant volume, but the shape is whatever. Particles are free to move, but they do interact. A gas, shape of the container, volume of the container. Particles do not interact, and they're very far apart. Then also there's pure substances and mixtures. Pure substance is one thing. It can be made from more than one thing if it's a compound, or made from one thing if it's an element. A mixture is more than one thing in the same container. So very clear, a compound is one thing made from more than one thing. A mixture is more than one thing, and it's just more than one thing. Homogeneous means it looks like the properties are evenly distributed or evenly mixed. Heterogeneous, not evenly mixed. Okay, a couple other things. When we talk about these properties, there's 2 different types. There's physical properties and there's chemical properties. So if you think of a person and want to describe your properties, your physical properties would be your appearance, right? So it's just something you don't have to change what it is to figure it out. So, what color is it? What's its shape? What does it smell like? Or what's its density? What temperature does it boil? What temperature does it melt? Chemical properties are behavior with other substances. So does it burn? It would be like its personality. So, whoops, sorry. So this is just another description. Okay, physical properties can be determined without color, melting point, that kind of stuff. But it's still the same substance. If you look at the little models here, see it's still the same substance. In chemical properties, you have to do a reaction, and when something goes through a reaction, it's not the same. So chemical properties, does it react with oxygen? The answer to that question would be a chemical property. And then matter undergoes changes, and we use the same classifications. A physical change is a change without changing the identity. So if you boil water, water liquid, water gas are the same compound. So that though we call it something different, it's a physical change. Chemical change means you've made new stuff. And how do you make new stuff? Well, you rearrange the atoms. Okay, so this is a nice picture. This is a physical change, but you can see the molecules themselves are exactly the same. So some types of dissolving, for example, okay, boiling, melting, cooling, taking a piece of paper and ripping it in half would all be physical changes. Chemical change is when you make new stuff. So you're going to see a difference in properties. So color changes, heat or life given off, not always. Smell change, taste change, makes a noise. Okay. Bottom line is you made new stuff. Now, a couple things. We talked about the law of conservation of energy in the last set of slides. Similarly, there's the law of conservation of matter, and this was demonstrated by Lavoisier. He did experiments in sealed containers, and I would not do that because it's dangerous. Matter can change form. It can't be created or destroyed. So during a chemical change, right, I have 100 grams of this compound, 92 grams of this, right? And when this breaks down, I get 92 and 7, and this adds up to the 100. Right? So the total amount doesn't change in a reaction, just rearranges. Okay? Now in a chemical change, new substances are formed, but it's all there. Where did it come from? It came from the old substance. So basically the total amount of particles doesn't change, they're rearranged. So for example, if we take hydrogen gas and oxygen gas and we form water, you can see there's still 1, 2, 3, 4 hydrogens. 1, 2, 3, 4 hydrogens and 2 oxygens. As far as writing formulas like this, we'll deal with that much later. Okay, but I just want you to see how matter is conserved. Now, this is kind of the last thing we're going to talk about on this set of slides. As I said, there's the law of conservation of energy and the law of conservation of matter. And those came out in, you saw 1700s for conservation of matter. Conservation of energy was around that time. In the early 1900s, it was discovered that you can actually change matter into energy. This is how nuclear energy works. And we're not going to get into nuclear energy in this class, but that's an example. And origin of the universe theory, energy changed into matter. So that's only been done once. But what this does, it says the law of conservation of energy is broken because we're making energy and we're not making it from energy. And matter is destroyed and not being made into matter. So both of these laws turned out to be wrong. So what do? When we have a scientific theory, a law is just a good theory. What do? We tweak it. So whoops, we updated the other laws. And so what we have, make sure I didn't skip a slide, we updated it to the law of conservation of matter and energy, which says the sum of them is constant. They can interconvert. Now, why did I spend a couple of slides and several minutes explaining law of conservation of energy, law of conservation of matter, and then I said, oh, guess what? I was lying to you. I want to point out that after hundreds of years, new information came out and said, guess what? We were wrong. There's something we didn't know that we know now. And so we revised our theory. Right? And that happens in science. It does. New information comes out, and we have to change the way we're thinking. All right. However, I do want you to realize that though matter changes into energy all the time, it's only significant, like you can measure it in nuclear reactions that we're not going to deal with. So in general, those other laws are true enough. So if I had 5 grams of iron and I combine it with 4 grams of oxygen, I'm going to get 9 grams of the compound. Okay, or if something loses mass, it didn't lose mass, the mass didn't become. If I had 50 pounds of wood and I burn it and now I have 2 pounds of ashes, where do the other 48 pounds go? It did not get converted into energy, it got converted into a type of matter that just left the container. So in general, these laws are true enough. One other thing though, it suggests if matter and energy can be interconverted, it suggests that perhaps matter and energy are not really different things, but different ways of looking at the same thing. That idea of matter and energy being different ends of a continuum, that's going to come up when we discuss the model of the atom. So we're going to look at that. Stay tuned. That will be coming soon to a lecture near you. All right, so that's it for this set of material. At this point, you should have enough information to do homework 1, and in this module, you'll be able to see the due date for homework 1, and all that information's been explained before. All right, have a good one, and you know how to reach me if you have questions.